Okay, so we're going to look at some periodic trends since we're talking about periodic things, right? So one of the trends that's can be deciphered from the periodic table is the size of atoms. So we first have to decide how are we going to define the size of an atom, because we draw them a lot. You know, these look a lot like marbles or ping pong balls or something, right? But atoms don't actually have an outer surface. They're fuzzy, right? The outside where the electrons are is just this region of probability. It's this wave particle thing going on. And so how do you put a boundary on that? Well, we have different definitions. I just want you to be aware of these. I'm not going to quiz you on them or test you on them. The non-bonding atomic radius, also called a van der Waals radius. So this would be something like here where we've got a solid, and what we're measuring is the distance from one nucleus to the next nucleus. Because you can identify where the nuclei are. It's complicated, but you can do it. And so you can measure the distance from one nucleus to the next nucleus, and then we'll say, well, the radius must be half of that. Makes sense. Another way to do it is to look at a bonding atomic radius or a covalent radius. So here we're looking at a molecule, not a pure solid, but a molecule. And again, looking at the distance between the nuclei and dividing that in half. This bonding radius is going to be smaller than the non-bonding radius, because when atoms covalently bond together, that pulls them in closer, because they're sharing electrons. The electron clouds overlap, and so that's smaller than the non-bonding radius. What we'll look at, we'll talk about is sort of a generic term, atomic radius. And the way they would quantify this is they'd take an average radius based on measuring different elements in different forms and different compounds and kind of put them together and come up with sort of an average. This is going to be smaller than the non-bonding van der Waals radius, but it's just kind of a general term. We are sometimes interested in how long is a bond between two atoms. We can approximate that by just adding the radius of the one atom in the bond to the atom of the other, the radius of the other atom. And that'll give us an approximate idea of the bond length. To get an actual bond length, you'd have to study that particular compound. So let's look at the trends in atomic radius. Now we know that what atomic radius means. But what we see is that atomic radius decreases as you go down a group. So a group, remember, is a column in the periodic table. So this graph can be confusing. We're looking at atomic radius versus atomic number. Yeah. It increases down a group. Did I say decreases?
Yeah.
Sorry, brain fart. Okay, atomic radius increases down a group. Apparently I can't read today either. So here are the alkali metals. So lithium, sodium, potassium. They are in a column in the periodic table. And so going from lithium to sodium, potassium, rubidium, cesium, we see that the radius increases. If you look at the noble gases, helium, neon, argon, etc., we also see that it increases. It's not linear, but it does go up. And when we're talking about when we're talking about periodic trends, they are just trends. There are sometimes exceptions. If you look at within a period, so the periods are the rows. So if we look at lithium going across all the way to neon, what we see is initially there's a big decrease in radius, and then there's a slight decrease with the last one. So it's not at all linear. And you get to neon, and then it jumps way back up to sodium, and we see that trend go down again to the noble gas, and then it goes up to potassium. So there's this trend from the alkali metals to the noble gases that the radius gets smaller.
So it increases as it goes down and decreases
as it goes across. And what's most important, I think, is to understand why it decreases. Because if you understand why, then you can reason it out. I have a hard time connecting down is increasing and across is decreasing. I mean, it's just two pairs of things and you could match them up either way and it's easy to get it wrong. So I prefer to understand what's going on and failing that, come up with some silly explanation that I can remember. So increasing going down should make sense. I think, yeah, here's a periodic table. So as we go down, here are atomic radii. So here's lithium 152, sodium 186. We see it's going down. Well, what are the electrons doing? Where are the electrons? Well, lithium's valence electrons are in the second energy level, the third energy for sodium, fourth energy level for potassium, fifth energy level for rubidium. As that principal quantum number increases, 1, 2, 3, 4, 5, those electrons are on average farther from the nucleus. So it makes sense then that as you go down, it gets larger. You okay with that? What does not make intuitive sense is why does it get smaller as you go across? Because we're adding electrons, we're adding protons. Neon weighs more than lithium. Why is it smaller? Well, quantum mechanics explains this. And it has to do with effective nuclear charge. So we talked about shielding and how when there's more than one electron in an atom, we've got attractions between the electrons and the nucleus, and we have repulsions between the electrons. And the outer electrons get shielded from the charge of the nucleus by the core electrons. So the outer electrons do not have as much attraction. And here's that diagram again. So here's lithium. Nucleus is +3 charge because there's 3 protons. There are 3 electrons. These are the core electrons in the 1s sublevel. And then here's the valence electron in the 2s. On average, the 2s is larger, farther away from the nucleus. So when this looks at the nucleus, these 2 electrons shield it from the charge. And so the effective charge for this electron is a +1 instead of +3. And just a reminder of Coulomb's law. This is going to come up a couple of times today. That's a really bad too. The attraction between charged particles, oppositely charged particles, depends on the charges. So if you have the electron being -1 and the nucleus being +3, that product is -3. But if this is +1, now the product is +1. And so this is experiencing only a third of the attraction that the others are. So less attraction means that the electron's going to be further out. More attraction means it's going to get pulled in. We can calculate, or it's not much of a calculation. We can estimate the effective nuclear charge. We call it ZF. Z effective is going to be the atomic number, the actual nuclear charge, minus the number of core electrons. To figure out the core electrons, you look at, well, how many valence electrons are there? How many total electrons are there? And the core electrons are the ones that are not valence electrons. So let's look at the effective nuclear charges for nitrogen and argon. And actually, I'd like to do nitrogen and neon instead because I do. So we're going to do neon instead. So for nitrogen, the effective nuclear charge is going to be the atomic number, the number of protons in the nucleus, which is what? 7. 7 protons, minus the number of core electrons. So if we look at the electron configuration for nitrogen, 1s2, 2s2, 2p3, right? So these are the valence electrons, and these are the core electrons. So there's 2 core electrons. So 7 minus 2, so we've got an effective nuclear charge of 5 for nitrogen. Let's look at neon. How many protons does it have in its nucleus? 10. And if we look at the electron configuration, there's the electron configuration for neon. These are the valence electrons, and here's the core electrons. We take the charge on the nucleus and we subtract the number of core electrons. So -2 equals 8. The valence electrons in neon experience an effective nuclear charge of +8. In nitrogen, the effective nuclear charge is +5. Valence electrons in neon are more strongly attracted, and so they get pulled in. If we look at where the valence electrons are for nitrogen and for neon, here the valence electrons are in the second energy level. Here the valence electrons are in the second energy level. There's no intrinsic difference between how far the electrons are from the nucleus based on the energy level. They're all in the second level. They're going to be roughly the same distance. So then we'd say, well, these atoms should be the same size, but this has a higher effective charge. Yes?
Is it just coincidence that the effective nuclear charge is the same as the valence electrons, or is it always going to be?
That's a good question. Is it a coincidence that the effective nuclear charge is the same as the number of valence electrons? No, it really isn't. It's not really a coincidence.
Is it always going to be that way?
It will not always be that way. It depends on, if you get into the larger, if you get it gets complicated when you get to bigger elements. I don't want to commit to anything. Much of the time it's going to work, but I don't want to commit to that or think too hard about it. Any other questions?
Is there anything in all of chemistry that is always?
Is there anything in all of chemistry that is always? There are lots of things. What we remember is the things that are, well, it's mostly this, but then there's that. Protons are always found in the nucleus of the atom. Electrons are always found outside the nucleus. Okay.
We haven't found a way to mix that up yet.
No, can't mix that up. It's kind of like the Ten Commandments. The Ten Commandments say, don't do this, don't do that. That's a short list. And then there's like this infinite list of things that you can do, right? So we are more aware of these exception things. I wish that everything could just be, oh, it's this way and this way and this way. No exceptions. But I guess that would be boring.
In radiation, aren't the protons?
Well, in radioactive decay, protons can leave the nucleus, but in an atom, they're not going to be found outside the nucleus.
They can be found outside the nucleus.
They can be found outside the nucleus,
And not with atom being the same thing.
but yeah. So, it's just details in the language, right? That's why I've been trained to be, at least try to be very precise in how I say things, because I'm very aware of all of these other things that could be misinterpreted. Okay, so back to the trend in atomic radius. It's okay. As you go down a column, principal quantum number is increasing, and that gives us larger orbitals and understandably larger atomic radius. This one people don't have trouble with. It's going across the period. The effective nuclear charge is increasing because the number of core electrons stays the same as you go across a period. You're adding valence electrons, but you're also adding protons, right? So more protons, same number of core electrons, higher effective nuclear charge. That higher effective nuclear charge pulls those valence electrons in tighter, and so we see a smaller radius. Any questions? Now the transition metals, at least they're consistent in being exceptions to stuff, right? We do see the trend down a column of increasing, but when you go across, things are really unpredictable. There's really not significant differences as you go across the D block for the transition metals. Part of that is because the effective nuclear charge is approximately the same for all of them. We got to do something here. I think I talked about iron yesterday. I think I'll talk about nickel today. Nickel is D8. So let's just look at the electron configuration for nickel. So 4s2, 3d8 on top of the previous noble gas. How many valence electrons? Highest level is 4. Yeah, trick question. So 2 valence electrons, right? These are core electrons. So
Would you count 1s2 and 2s2 and all that too?
those would be core electrons also. So if you look at nickel, nickel has how many protons? 28. So 28 protons. So let's look at its effective nuclear charge. So the effective nuclear charge for nickel would be 28 minus the number of core electrons. Well, there's 2 valence electrons. So there's 28 total electrons, 2 valence electrons. That means the rest of them are core electrons, so that's 26. So the effective nuclear charge is 2. Let's look at zinc. So the effective nuclear charge for zinc, how many protons does zinc have? 30 protons. And if we look at its, oh well, I'm mixing this up because I can't see what I'm doing. Its electron configuration is 4s2, 3d10. How many core electrons does zinc have? 28. It has 2 valence electrons. It has 30 total electrons, 2 valence electrons, so the difference is 28. Those are the core electrons. So 30 minus 28 equals 2. The effective nuclear charge for nickel and zinc is the same. The electrons are in the same levels, principal levels, and so based on looking at this, we'd predict that there's no difference in size. That's roughly correct.
So is there any transition metals that don't have?
There are. So remember we learned about the exceptions, like chromium and copper. So copper's right in between. Let's stick copper up here. So we would expect that copper would be 4s2, 3d9, right? But this was an irregular electron configuration. It turns out there's this deal where if you put this electron up here, get that right now? If you put one of these electrons up here, then it's more stable. And so it actually is 4s1, 3d10. It's one of those. Yeah, so that's what we expect, but this is what it actually is. So copper, its effective nuclear charge, well, it's got 29 protons, 29 electrons. How many valence electrons? 1. So then it's got 28 core electrons, and so its effective nuclear charge is 1.
So that line kind of pretty much is over when you're talking
Pardon me?
over 1 on copper or just copper?
It's just copper and chromium that are weird. But as you go across, the effective nuclear charge is mostly the same. It's not like in the main group where it's increasing by 1 as you go across. And if we go back to this graph, here in the green, here are the period 4 transition elements. And there is some trend here. It's going down a little bit. But like these guys are all really close to the same size. And so we don't see the same sort of trend that we do going across from like lithium to neon. So it's less of a trend. Any questions?
Oh, actually, I do have a question.
Okay.
Is there an element that you know of that has a effective nuclear charge that isn't equal to how many valence electrons it has? Because everything we've done so far has been the same amount of valence electrons.
I can't think of one off the top of my head.
So
Mostly.
Can we just skip that then? And
Well,
just look at the effective nuclear
So
charge?
this is a simplified calculation for effective nuclear charge. There's actually one that's more accurate. It's a little more complicated. But we're not going to go there.
Yay! So for
Yay!
now,
So
we can
so just be happy with this, right? It's mostly the same as the number of valence electrons. But it's helpful to understand why that is. Okay. So what should you be able to do with this? You should be able to answer questions like this. On the basis of periodic trends, not looking at a table of actual atomic radii, but just based on trends, which one's bigger? So the way we do this is we find the elements in the periodic table. So we need tin and iodine. And since I don't have a periodic table up on this slide, I'm just going to draw them in here. So there's tin and iodine. You're just interested in where they are relative to each other. So we see that iodine is to the right of tin. They're in the same period. So we're looking at this trend. What happens as we go across?
decreases.
It decreases. Because the effective nuclear charge is increasing and it's pulling those electrons in tighter. So iodine is smaller than tin. The question is, which one's larger? It's the tin. And that's exactly what would go through my head if I had to answer this on a test. I would think it through. I don't just automatically remember these trends. Okay, germanium or polonium. We'll find them on the periodic table. You don't have to know their names, just be able to spot them. Okay, so here's germanium, and here's something else, and then polonium's down here. There was a Teletubby named Poe. So what's going on here? Well, we've got a trend going across, and we've got a trend going down. So the trend going across predicts that which one is larger? Germanium. The trend going down predicts which one is larger? Polonium. The trends are opposing each other. Do you see this if possible? Yeah. The small print up there. So a perfectly acceptable answer here, not possible. Can't tell. Now, what if they forced you, like a multiple choice, they forced you. They didn't give you not possible as an option. And what do you do?
Leave it blank.
Leave it blank. Then you know that you're going to get it wrong. What was your...
Trend tends to be stronger.
Yeah, that's the question. Which trend tends to be stronger? So when we're going across, we're adding electrons in the same principal energy level, but the effective nuclear charge is pulling them in a little bit more. When we're going down, what's happening is that we're adding to a new level. And this is where having the Bohr model of the atom in your head, even though you recognize that's not actually how it is. Let me just draw it over here. So here's our nucleus, and here's level 1, and here's level 2, and here's level 3. It's getting too big. So if I've got an electron here or an electron here, which one's going to be farther from the nucleus?
The second.
The second one, this one. In the higher energy level, the higher principal level. So going from germanium down to whatever that was, to polonium, we're going up 2 levels. And so this is probably going to be a much bigger effect than going across. So if I was forced to choose, I would choose polonium. Does that make sense?
On a test, are we going to be forced to choose?
I haven't written the test, I don't know. And that would depend on my mood at the time when I write the test.
Remember this moment, please.
I'm just being honest. Okay, so chromium or tungsten, it kind of looks like crow. Let's find those guys in the periodic table. CR, where'd you get? There you are, CR and W. So they're on top of each other. There's CR, there's W. Oh, that's nice, it's not diagonal. What's the trend going down?
It's big.
Gets bigger. So which one's bigger, chromium or tungsten? Tungsten. Any questions?